Good afternoon, everyone. Am I audible? Please respond. Am I audible? Is my voice clear? Okay. As part of the series of these classes, in today's session, we are going to discuss about the processes and processes scheduling. So let us start with the process and what is meant by process and what is the difference between a process and a thread. And in today's session, we will be discussing some terminology about CPU scheduling. Okay, so let us start with the processes and threads. See, the main objective of this today's session is to make you understand the processes and the threads in operating system. And
Sir,
we will
excuse me,
yes, please.
sir, third semester, sir.
Yeah, it is third final year for fifth semester.
No, sir, third semester. There's a link. Third semester అని ఉంది కదా sir.
That is third year and fifth semester. Okay.
No, sir. Use it third semester. Computer applications is showing.
Yeah, sir. Okay. The the processes and threads in operating system. And so we'll be understanding how the process each other will be discussing process schedule, will be discussing different types of we know when we use a computer, the computer with some softwares and it's called as a program. And if you want to, if at all you want to use so whenever you start any application program system, first the application program resides in your secondary memory, that is hard disk. And if you want to run that software, it must be loaded from the secondary memory into primary memory. So that is also called as the main memory. Okay. So when an application programs initiates, actually the program loads from, that is loaded from the secondary memory into primary memory. So that means when an application program is loaded from the secondary memory into primary memory, it is known as the process. Known as the process. So now we can define a process as an instance of a program. A process is actually a program which is under execution. That means the program or a program so which is loaded from the secondary memory into main memory, that is called as the process. And it is also called as the text section, and that include the current activity as represented by the program counter and the content of the CPU register. That means the process has several attributes, and we'll be discussing them later. That means whenever a program is loaded from secondary memory into primary memory, so that is known as the process. I mean, the process is nothing but a program which is in execution process, which is under execution. And every process has several attributes like the process stack. Here, the process stack is one element of the process that actually stores the temporary data. So where local variables and the global variables are stored on that stack. And it also has the heap memory. The heap memory is actually for dynamically allocating the memory for the variables. And it also contains, the process also contains several attributes, and we'll be discussing about them. Actually, there is a small difference between the process and the program. The program is actually simply a passive object, and whereas a process is an active object, because the process is actually the unit which is under execution, whereas the program is a passive object which resides in the secondary memory, okay, which is not active actually. So when the program gets activated, it's called a process. So the process is nothing but an active object. So when a process is created, that means when a program is initiated, when this application is started, the application is, as I said, the application is loaded from the secondary memory into primary or main memory, and that means the process is now created. So in the creation of the process and the termination of the process, the stage can be existed. So this is all a life cycle of a process. So like human being have several stages, the process also have several stages during its lifetime. That means from the of the ending of the process. So let us see what are the various states of a process in any of these 5 states during its life cycle. So the first state of the process is the new state, and second is ready, and third is running state, and fourth is waiting, and finally it will move to the terminated state. And let us see when a process is said to be in the new state. Process is said to be an application is loaded from the secondary memory to the main memory. That means the process is created, and now it is said to be a new state. That means a newborn state. A process is created. So once the process is created, it doesn't mean that it is directly executing. So if it has to execute, it needs the CPU. So once the CPU is assigned, it starts its execution. That means as soon as it enters the main memory, it cannot start its execution. First, it will move to the ready state. The ready state is here. In the ready state, all the waiting for the CPU. Once the CPU is available for a particular process, immediately that will move to the running state. That means the process gets executed. Okay, so first the process enters the new state when the process is created. As soon as the process is created, it doesn't really mean that it executes. First, it has to enter into the ready state where all the processes must be waiting in the wait queue. That is nothing but the job queue here. All the processes waits in this. So they wait for what purpose? They wait for the CPU allotment. See, the process, when they move to the ready state, and once they get the CPU, immediately they enter the running statements. They are running. They starts their execution. So that is called as the running state. So, and if at all any process requires any input, if at all if the process wants to send any element to the output devices, that means the process is interrupted. The process is interrupted. So that means the process must be moved to the waiting state. So while it is running, the process may need some input. For example, while you are executing any program, the program may need some input. See, until you enter any input, the program waits, right? So program must wait. So as soon as you enter that input to the program, again it resumes its execution. That means, so while it is executing, the process needs some input or the output. So while it is taking the input from the user, while it is reading the data from any file, must be waiting. So during the time, it will be getting into the waiting. See, while it is in the waiting state, so again, if it tries to run again, it is not directly possible to run. So again, it should move to the rest state to the CPU to get the CPU. So that means when the CPU is created, first it will be in the new state, and so that will be sent to what? Ready state. In the ready state, all these processes will be waiting for the CPU. Once the CPU is available for a particular process, and once the CPU is allotted for a particular process, then it starts its execution. That is called the running state. And while it is running, so it may either enter into waiting state, and if there is any interruption, the interruption may be done by the IO, or interruption may be any preemption. Then again it may move to the ready state. For example, the process has executed all its process is executed all its task. That means process execution is completed. Then it will move to the terminated state. Terminated in the sense the process is removed from the main memory. Okay. So once it enters the terminated state, in the sense the process is removed from the memory. That means CPU is released from that particular process. Okay, let us see all these processes now. That means the new state means the process is being created. When the process is created, when an application program is initiated, as I have said, the application program is loaded from the secondary memory into main memory, then a process is created. So that is called as the newborn state or the new state. And what about the running state? If the running state is nothing but the process when it starts execution, so that is called the running state. And from that running state, either it may enter the waiting state, or it may enter the ready state or the terminated state. See, when it enters the waiting state, the process may enter the waiting state, or the process is said to be in the waiting state when it is waiting for some event to occur. So what about the event? The event may be the IO. That means it may be input interrupt or output interrupt, or it may be waiting for any data from it may be waiting for any say any operation like writing data to a file. These are all the reasons the process should be in the waiting state. And what about the ready state? The ready state means all the processes waiting in that job queue, all the process which will be waiting in that state only to get the CPU. And what about terminated? Once the process has executed its all instructions, that means the process execution is completed. So then we say the process is terminated. So these are the 5 states a process can be in during its life cycle. Okay. Okay, students. So a process, as soon as you initiate any application that enters the new state, that means the new state is nothing but the newborn state. The process is created newly. Okay, so then it enters the running state. When it enters the running state, as soon as it cannot enter the running state, first it will move to the ready state. So ready state means it is waiting for what purpose? CPU. So the CPU may or may not available. So once the CPU available for a particular process, now it can enter the running state. The running state is nothing but now the process can start its execution. It can start executing its instructions. And during, so that means while it is in the running state, either it may move to waiting state or it may move to ready state. So there are the two choices. Either it may be moved to the waiting state, or it may move to the ready state, or it may be terminated. So when it is terminated, once the process has executed its all instructions, then it is terminated. That means the process is completed and it will be, so the CPU will be pulled out from that particular process. So this chart or this diagram shows the life cycle of a particular process. The process is created, that is a new state, and then it enters the ready state waiting for the CPU. So then the CPU is available and the CPU is allotted for a particular process. Then it enters the running state. Running state is nothing but the CPU is, so that now the CPU is available for the particular process and the CPU is executing that particular process. The process is now executing its instructions. That is the running state. So once the process has executed all its instructions, then it is nothing but it is close. So then it enters what? Terminated state. Okay, so this diagram shows what all the states of a process of its life cycle. And see, PCB, very, very important component of every process, the process control block. What about the process control block? Every process is assigned with one important element, that is PCB. PCB stands for process control block. Here the PCB is actually an element that is added by the operating system to every process. So where the PCB contains what? The information about the particular process. What kind of information it contains? It contains the information about the process state, whether it is in ready state or whether it is in running state, whether the process is in waiting state. So the state of the process is denoted by this process state. That means process state is one attribute, so which is in the PCB of the particular process. And the PCB also gives the information about the CPU registers. That means currently which registers are activated and which register it is using. And CPU scheduling algorithm. So the process may be using the different types of scheduling algorithms. Either it may be FCFS or the round robin or preemptive or non-preemptive. What kind of scheduling algorithm it is? It is using now. That information is there in this CPU scheduling algorithm. Next, memory management information. So here the memory management information shows what? So whether process is using any file, whether so it is using any data, whether it is using any directory. So the total information is available in the memory management information block. And accounting information, the PCB also gives account information. That means how much memory is remaining and how much memory has been already used. So that information is nothing but accounting information. IO status information is also provided by the PCB. IO status in the sense whether the process is waiting for the input or whether the process is waiting for the output. That is IO stated information. That means the PCB gives the total information about a particular process. So it gives the information about the state of the particular process and currently which registers have been assigned to the process and which scheduling algorithm is used for the particular process. And what about the memory management? That means which files are linked to that particular process, and account information, that means how much memory has been already used and how much memory is available. So that is the accounting information, and how many resources are available and how many resources have been already utilized. That is accounting information. And IO status means whether the process is waiting for input and output. So that is the PCB attributes. So the PCB gives all these attributes. Just look at this diagram. It shows the information about the PCB. as I have shown you just now, the PCB contains all these attributes, process state and the process number, that is called as the process ID, and the program counter. The program counter is nothing but, so it shows the next instruction to be executed, And register, it gives the information about the CPU registers which are in usage, and the memory limits. So that means how much resource have been already utilized and how much resources are now using. And the list of open files, that means whether the process is accessing any file, the file information will be given here. So like that, the PCB gives the information about a particular process. And on the right side of this picture, you can see, for example, here the two processes are under execution, process P0 and the process P1. While the process P0 is executing, and if it is interrupted, so it is interrupted for some reason. For example, the process may be interrupted for some reason. So generally, the process may be interrupted because of the reason like the IO. That means, for example, while the process is executing, it may be demanding for some input. That means that is interrupted. So when the process is interrupted, immediately the process state must be saved into the PCB. Okay, so that's how many instructions of that particular process has been executed till where, that is the state. So the state must be saved into the PCB, so that the process, when it is resumed, and from that particular instruction it should be resumed. So that is, the saving the state is important for a particular process, so that when it is to be resumed again, it should not start from the beginning. No, it should be started from the place where it is left. So that is, the process, while it is executed, it may be interrupted, or it may be interrupted by any system call. It may be waiting for any input, or it may be sending the data to any output. Okay, so by any system call, read or write or any kind of operation. So then the state of that particular process must be saved into the PCB. Okay, so now it is waiting for the input. Let us just assume, while it is waiting for the input, until it gets the input, it cannot continue. It cannot continue. It cannot continue. So that means the process is now idle. It is not executing any instruction. It is waiting for. So during that period, what the operating system will do is immediately it execute the process P1, which is already in the ready queue. Chooses one of the process from the ready queue, so which is waiting for the CPU. So one process will be selected from the ready queue and it starts its execution. Okay, see, first the process P0 has got the CPU and it has executed for some milliseconds of time. And since it is waiting for some input, and during that time, immediately, so it picks up another process P1 from the same ready queue. Let us assume the process P1 has picked now. Some process P1 has picked now. So immediately the process P1 is reloaded from the PCB. That means the reload the state from the PCB1, and it has started its execution. And just assume the process P1 also interrupted by some system call. So again, the process state must be saved into the PCB1. Like that, the process has to be switched from one to other. While one process is executing, another process should be wait. And see, while one process is waiting, so another process can be selected from the process pool and it can be executed. Like that, the process can be switched. This is called the context switching. The context switching is actually done by the CPU scheduler. According to the CPU scheduling algorithm, the context switching occurs. So here, what plays an important role? The PCB plays an important role. So because the process is not continually getting executed, the processing is getting executed for some amount of time, and immediately the CPU is giving the chance to another process. That means the state of the process must be saved into the PCB. That means here PCB is playing an important role. The PCB is saving what? The state of a particular process. So how much process, that means till which is instruction it is executed and how many instruction are to be executed. The information will be available in the PCB. That is the process state. So the process number gives what? What is the next instruction to be executed? That is the process number. So like that, the PCB gives what? Complete information about the process while it is executing. And when it enters the waiting state and when it has to be resumed, so the PCB plays a vital role, right? The CPU uses the PCB or the scheduler uses the PCB. So when the process has to be resumed, when the process has to be moved from the ready state to running state and running state to waiting state. So that means from one state to another state, when a process has to be moved, it must use what? The PCB information. So based on that PCB information only, so it will resume a particular process or it may terminate a particular process. So that is the PCB. Now let us talk about the process scheduling. What about the process scheduling? So the process scheduling, before knowing about the process scheduling, first what you need to understand is the process and the thread. There is a small difference between the process and the thread. So in the beginning of this session, I've already told you the process is nothing but the program which is under execution. So when you initiate any application program, when you start any application program in your system, that is loaded from the secondary memory into primary memory. That is the main memory. So when that is loaded into the main memory, that is actually called as what? A process. The process is nothing but the program which is in execution. And the process actually has a single flow of control. That means the process actually executed in the serial order, sequential order, one by one, the instruction by instruction it will execute. That is called as what? Single threaded program. And see, sometimes the process may have the multiple threads. Generally, a process may have the single flow, and sometimes the process may have the multiple threads. That means the same process may lead to the multiple flows of the execution. That is called as the multi-threaded programming. Now I'll tell you the difference between the process and the thread. The process is nothing but the program, which is actually loaded from the secondary memory into main memory. So that is for execution purpose. So that is now executing by the CPU, that is called the process. Generally, the process contains the single flow of control. And if the process with the multiple threads, actually the process may have the multiple threads. So that automatically increases what? The CPU utilization. How the CPU utilization can be increased? Because when the process has the single flow of execution, for example, the process is waiting for the IVO and there is only single flow of execution until it gets that input, the process must wait and it cannot give the chance to any other process. For example, there are two processes. Let us assume one process is now running and let us assume the process one is waiting for what? The process one has been interrupted and process one is waiting for the input. So while it is waiting, the process one cannot start because the process are executing one by one. The process are executing one by one. And for example, the process has to perform the several tasks and all these tasks should be performed in the sequential order. This is called as single flow of control, single flow of control. So, but when the process has the multiple threads, so these threads can be executed in the concurrent manner. Concurrent means so one flow and another flow and first flow and the second flow. So the control, that means the CPU can be allotted, the CPU can execute these two flows or the multiple flows simultaneously. This is called like the concurrent execution of a process. So when a process has the multiple threads, there is a chance of what? Executing the multiple flows. When then there is a chance of selecting the multiple flows. So the CPU will not be idle at all. While it is waiting for the input, immediately the CPU may select another thread and it can run. That means it is not in the ideal state. Okay, so the process, when it has the multiple threads, the CPU utilization can be greatly increased and the CPU will not be idle. You can make the CPU what? You can make the CPU always busy. That is the major purpose of what? The multiple threads. So let's talk about the thread here. The thread is not sorry for the interruption. So the thread is nothing but an instance of a process where the process can have the multiple threads, and each thread is nothing but an instance of a process. Okay, so each thread has several attributes like the process has. The thread has several attributes like thread ID, and it has the program counter and register state and the stack. And your threads may be intercommunicated for sharing the data and sharing the code also. That is called as the inter-thread communication. Okay, sometimes, so one thread may share the data with another thread, and it may share the logic or the code with another thread. So this is called as what? Inter-thread communication. So the major purpose of the multi-threading is to increase the CPU utilization. So to improve the CPU performance, improve the system performance, so only thing we need to do is we should increase the CPU utilization. How can you improve the CPU utilization? We need to make the CPU always busy. It should not be idle. So if it is idle in the sense, the system performance will be degraded. So if the system performance has to be increased, then the CPU utilization should be increased. So the CPU utilization can be increased by multiple threads. So let us see the single threaded programming and multi-threaded programming. So as I was said just now, generally the single threaded programming is nothing but it has only single flow of execution. So only there will be one control. That means this instructions are executed in the sequential order, right? So once, until and unless one flow of execution is completed, it will not move to any other block. So that is called as what? Single threaded programming. It is a single flow of execution. Whereas in the multi-threaded programming, generally a process may contain the multiple threads. Most of the operating system supports what? Multi-threaded programming. So where the process may have the multiple threads. So these multiple threads can be concurrently executed. These multiple threads can be concurrently executed by which process? Context switching. Here the context switching is nothing but. So here, since there is only single processor, the processor or the CPU it has to execute the multiple threads. No, it has to control the multiple flows of execution. Since there is only single processor or single CPU, so it must be switched and it should control the execution of the both So it should execute the both flows at a time. So there is only a single processor, but it has to execute both the threads simultaneously. Generally, it won't occur. This is just the logical concurrency. It is not a physical concurrency. Logical in the sense. So we may feel that all the threads are concurrently executing, all the threads are executing simultaneously, but it won't happen. So this is just logical concurrence. See, here the logical concurrency is achieved by the context switching. Context switching is nothing but, see, switching the CPU between the multiple threads according to the CPU scheduling algorithm. So that is called as what? Multi-threaded programming. Just look at this diagram, you can easily understand there is a small difference between multi-programming and multi-threaded programming. In the multi-programming, so there will be multiple programs which are loaded into the main memory, and these programs are executed and controlled by the CPU. That means the context switching is done among all these programs. This is called as the multi-programming. Okay, the multi-programming allows you to uh, work with the multiple applications simultaneously. That means you can switch from one program to another program. The CPU allows the CPU automatically switches from one program to another program. That is called the multi-program. Whereas the multi-threaded program, so one program may have the multiple threads, and the context switching is done between the threads inside the program. Okay, within the same program, if there are the multiple threads, multiple flows of execution, that is called as the multi-thread. Okay, multiple threads. So these multiple threads can be executed simultaneously by using which mechanism? Context switching mechanism. That means the CPU so is responsible for switching between the threads. Okay, so just assume these are the two threads. These two threads has to be executed simultaneously. So if the two threads has to be executed simultaneously, the CPU will the CPU switches between these two threads so that we can feel these two threads are executing simultaneously. Okay, this is called as what? A multi-threaded programming. So now let us see what is CPU scheduling. Here the CPU scheduling is a process that allows one process to be executed while the CPU is executing any other process. Okay, see for example, there are the multiple processes in the ready queue, and but we cannot run all the process simultaneously. We can run only one process at a time. So even though all the processes are loaded into the main memory, it doesn't mean that all the processes can be run simultaneously. So there should be a controlling mechanism in such a way that the process should be run in the concurrent manner. Okay, so while one process is getting executed, another process should wait, and while one process is waiting for some input or output, the CPU should not idle. So immediately the chance should be given to another process, and this kind of mechanism is called as what? CPU scheduling. So this CPU scheduling, the major objective of the CPU scheduling is improve the system performance. That means the productivity can be improved. That means the system performance will be highly increased by using what? The CPU schedulers and the CPU scheduling process. Okay, so if there are the multiple processes, these processes should be concurrently executed. Concurrently in the sense one process is going into the waiting state, and immediately the CPU should not idle. So in the meanwhile, the CPU should select any other process in the process pool and it should continue its execution, so that the some job has to be performed and the CPU should not be idle. The CPU should always be busy. Okay, so this mechanism is called as the CPU scheduling. The CPU scheduling allows what? All the processes are executed in the controlled manner. Okay, so in a controlled manner, in the concurrent manner. So that is the purpose of this CPU scheduling. And when we talk about these schedulers, there are two types of schedulers. There are two types of schedulings. Okay, so preemptive and non-preemptive schedulings. What about the preemptive scheduling? So these are the two types of the scheduling processes. So in case of the preemptive, the preventive in the sense it allows running process to be interrupted by high priority process. For example, the two processes are there, P1 and P2. And if the P2 has the higher priority than the P1, then before P1, even though P1 arrives before the P2, since the P2 has a higher priority, the P2 will be given the first chance to run. That means the preventive scheduling algorithm preempts one process. It preempts one process. Preempting is nothing but stopping one process and giving a chance to another process. This is called as what? Preemptive. So preemption allows what? See, while the two processes are executing, if you want to stop one process or stopping one process and giving a chance to another process to run, that is called as what? Preemption. This is a preemptive scheduling. And what about the non-preemptive scheduling? Here the non-preemptive scheduling is nothing but there is no priority, there is no higher priority, lower priority, and all the processes will be executed according to their arrival time, So that is called as what? A non-preemptive scheduling. Okay, so here there is no chance of stopping one process and running another process, and all the process will be executed in which order? In the order in which they are arrived. So that is called as what? Non-preemptive. Whereas in the preemptive scheduling, so one process can be preempted by another process if it has the higher priority. Okay, so if there are two persons, one person is very uh, important person and another person is a normal person, so then the high priority person will be given the first chance, okay, and the lower priority person will give the next chance. That means, so automatically the lower priority process will be preempted by the higher priority process. So that is called as what? Preemptive scheduling, right? So in the preemptive scheduling, one process can interrupt another process. So if it has a higher priority and it can continue its execution. So one process can stop another process from running and it can start running. Okay, that is a preemptive. Okay, so in the preemptive scheduling, generally when the preemption takes place. So here the preemption is automatically takes place in 4 conditions. The first condition is when the process switches from the running state to waiting state. Okay, it is a normal scenario or the general scenario. While one process is running, it may move to the waiting state. So when it moves to the waiting state, it may move to the waiting state. So when it is demanding for input or when it is waiting for any output, so immediately, so it is preempted. That means while it is running, it is stopping its execution and moving to wait state. So it is very general scenario, very common scenario. This is also one kind of preemption, but this is a non. So it is a non-preemptive condition actually. Okay, we are not for any other process is not forcefully stopping it, but itself it is ending into waiting state. So that is called as that is one condition where one process moves from one state to another state. So indirectly it is preempted. And second case is when a process switches from the running state to ready state. So it is again a common scenario. So while one process is getting executed, so it may be interrupted. It may be interrupted by any input signal. Okay. So if any input is given to the process, so it is interrupted and it is taking some input. That means now it is again going back to the ready state. That means it is preempted. So it is stopped temporarily and again it is moved to the ready state. So this is again preemption. Okay. And when a process switches from the waiting state to ready state. So again, for example, it is waiting for some input. Okay. So once the input is received by the particular process and it should again start its execution. So before it starts its execution, again it should move to the ready state. So again it is preempted. So that means whenever process transit from one state to another state indirectly, it is preempting. And finally, when a process terminates, so when the process completes its all execution, it will move to the terminate state. That means it is again moving from one state to another state. It is preempting. So the preemptive scheduling, generally the scheduling a decision is based on what? So based on these four conditions. Okay. So the preemptive scheduling actually based on when a process is running, the process can be stopped for a particular reason, and the chance will be given to another process, that is preemptive scheduling. And sometimes the process when it is running and it may itself enter into the waiting state. So for what purpose? For waiting for some IO or waiting for some event to occur. So that is called as a non-preemptive. And what about the terminate state? So when a process enters the terminate, when the process executes all its instructions, naturally it will enter into the terminate state. So that means we are not forcing it to stop. So itself it is going into where? So terminate state, that is called as a non-preemptive. So preemption is nothing but very simple. Here the preemption is nothing but so forcefully stopping one process and running another process. Okay, so while one process is running, so if another process comes, so if you want to stop that currently running process, and if you want to execute another process, then that is called as what? So then that is called as preemption. So preemption allows stopping one process from running and giving the chance to another process, that is called as the preemption. And what about the non-preemption? The non-preemption is nothing but, so once the process is allocated, one CPU is allocated to a particular process, so the process will not be, the process will not be leaving the CPU until and unless it finishes all its job. Okay, so in the non-preemptive scheduling, once the CPU is allocated to a particular process, so the process keeps the CPU until it releases the CPU either by terminating it or by switching to the waiting state. That means, so in the non-preemptive scheduling, so so once it enters into this running state, until and unless it finishes its job, okay, it will not leave the CPU. That means CPU will not be pulled out from that particular CPU. Okay, so it releases the CPU only when it finishes its all task, or so when it is demanding for any input or output, that means when it is moving to waiting state. That means, so it is not preempted by any other process. It is not stopping because of any other process. So this is called as what? Non-preemptive scheduling. And let us talk about the schedulers in OS. See, here the schedulers are nothing but one kind of special softwares. The scheduler is nothing but a small software, so which helps in scheduling the process in the different ways. That means the scheduler task of the scheduler is to select the job from the job pool and submit to the system and deciding which process to run. Okay, for example, when you start the multiple application, so these applications, when they are loaded from the secondary memory into main memory, so they are in the new state. Okay, so and they will be moved to the ready state and waiting for what? CPU. Okay, and here the CPU will be given to a particular process. So based on what? The scheduler. Here the scheduler task is for what? Selecting a particular job to be submitted to the system. That means, so which process has to be selected and which process should be run. So that decision is taken by the scheduler based on the scheduler algorithm. Okay. So when we talk about the different types of schedulers, there are three types of schedulers. Okay, so the first one is a long-time scheduler, and second is the short-time scheduler, and the third is the mid-term scheduler. What about the long-time scheduler? See, the purpose of this scheduling or the scheduler is to increase the degree of the multi-programming. Okay, so to increase the degree of the multi-programming. What about the degree of the multi-programming? So here the degree of the multi-programming is nothing but the maximum number of the processes that can be present in the ready state. Okay, and the multi-programming is nothing but the maximum of the maximum number of the processes that are loaded into the main memory and which are present in the ready state. That is called as what? Degree of the multi-programming. So if the degree of the multi-programming is high in the sense, you can execute the multiple processes at a time. Okay. So that means if the degree of the multi-programming is high, is nothing but your system supports multiple softwares to run simultaneously. Okay. So that is the degree of the multi-programming. And let us talk about the long-term scheduler. What about the long-term scheduler? See, the main objective of the long-term scheduler is to maintain the good degree of the multi-programming. Good degree of the multi-programming. That means when the system is installed with the multiple softwares, and if you want to run the multiple software simultaneously, then the degree of the multi-programming should be high. Okay, so that means the multiple programs or the multiple processes has to be loaded into the main memory. Multiple programs has to be loaded into the main memory, and they should be waiting in the ready state. They should be waiting in the ready state. Okay, so the major objective of this long-term scheduler is to maintain the good degree of the multiple programming. Okay, so the long-term scheduler is also known as the job scheduler. Okay, so it will select what? The IO bound and CPU bound process from the secondary memory. Okay, so the long-term scheduler task is to load the job or the program from the secondary memory into main memory. So that is the task of what? Long-term scheduler. Okay, so then after loading the process from the secondary memory into main memory, and then it starts execution. Okay, so there is a long-term scheduler task. And whatever the short-term scheduler. See here, the short-term scheduler is nothing but the main objective of the short-term scheduler is to increase the system performance. Okay, and how can you increase the system performance? See, by making the CPU busy. Okay, we cannot leave the CPU idle, right? So by making the CPU busy, we can automatically improve the system performance. So here the short-term scheduler is also called as the CPU scheduler, whereas the long-term scheduler is called as job scheduler, and the short-term scheduler is called as the CPU scheduler. Okay, see, when all the processes are loaded into the ready state, they are moved into the ready state. Okay, and so they are waiting in the ready queue. Now the short-term scheduler will decide the process. So that means it will select one process and the CPU will be allotted to that particular process so that it can start its execution. Okay, so short-term scheduler actually for the purpose of what? The context switching between the multiple processes. Context switching between multiple processes. So while both the processes are running in the running state, so while both the processes is to be run, right? So the context switching should be done. Here the context switching is the main job of what? Short-term scheduler. Okay, so that means it will decide which process has to run and which process has to wait and which process has to uh, resumed again, which process has to be waiting again. So the short-term scheduler will decide which process to be selected for running and which process to be selected for waiting. Okay, so that is short-term scheduler. And we have the midterm scheduler also. The midterm scheduler are for swapping purpose. Swapping is nothing but the swapping is needed. See, since the main memory is very limited, okay, all the processes cannot be stored in the main memory. Okay, so once one process is terminated, that must be swapped out from where? It must be swapped out from the main memory. So swapping is the major objective of what? The midterm scheduler. Swapping is nothing but what? So swapping out is nothing but what? Moving one process from the main memory. Okay, once it has finished its task. Okay, that is called as what? Swap out. Right, the midterm scheduler swaps out the process from the main memory to the secondary memory to free up the main memory when it is required. Okay, so the midterm scheduler reduces the degree of multi-programming. Okay, so that means once all the programs are loaded into the main memory, and at one point, see, the main memory may be full, right? See, and once one program is completed, that must be pulled out from that main memory. So yeah, the pulling out from that main memory is the job of who? The midterm scheduler. So the midterm scheduler, once one process is completed, so it will be taken out from that main memory and that is submitted to the secondary memory. So that is the task of the midterm scheduler. Okay. So here sometimes the swapping is also needed to improve the process mix, because all the process cannot be running in the main memory simultaneously. The main memory may not sufficient. So here the swapping in and the swapping out is the major task of what? Midterm scheduler. And what about the scheduling criteria? So if at all multiple processes is to be concurrently executed, so there should be a scheduling algorithm, and the scheduling algorithm based on the scheduling criteria. Okay, see here we will choose one particular scheduling algorithm based on this criteria, based on this factor. What are the scheduling criteria? Okay, see the scheduling criteria is CPU utilization, right? See here the scheduling algorithms have the different properties, and we can select any of the scheduling algorithm as per your requirement. Okay. So based on which criteria you can choose the scheduling algorithm, based on which criteria the scheduling algorithm works. So the first criteria is CPU utilization. CPU utilization in the sense to make the CPU always busy. Okay. See, to keep the CPU busy as possible. Okay, we should not keep the CPU idle. Okay, the CPU should not be idle while a process is waiting for the IO, so it should immediately pick up another process, okay, so that the process can be completed in the meantime. That means the CPU utilization, to improve the CPU utilization. Okay, so this is one criteria. The CPU utilization is one criteria. And throughput. Okay, so throughput is another criteria of the scheduling algorithm. We can consider this criteria throughput. The throughput is nothing but, so how many number of processes that are completed for unit of time. That is called as the throughput. For example, within 1 millisecond, how many processes have been completed? That is called as the throughput. If the throughput is very high, is nothing but the scheduling algorithm is very efficient, more efficient. Okay, and turnaround time. Here the turnaround time is nothing but, so it is the time of the submission of process to the time of the completion is the turnaround time. So that means when the process is submitted to the CPU, okay, and when the process is completed, the time difference, the difference between the process submission time and the process completion time is called as what? Turnaround time. So the turnaround time is small in the sense, the turnaround time is less in the sense, automatically the scheduling algorithm is more efficient. Okay, so we'll see the turnaround time, waiting time, bus time. In the further classes, you don't worry. So turnaround time is nothing but the interval between the submission of the process and the completion of that particular process. Okay. Next, waiting time. See, the waiting time is nothing but the total amount of time that is spent by a particular process in the ready queue. Okay, so that means as soon as it enters the main memory, it cannot get the CPU, okay, so it must wait until the CPU is available, until the CPU scheduler will assign the CPU to the particular process. Okay, so that amount of time is called as the waiting time. The waiting time is nothing but the sum of the amount, or the number of milliseconds, or the number of milliseconds the process waits for getting, or process waits in the ready queue for getting the CPU. Okay, and we also have the response time. Response time is nothing but the time it takes for the process to start responding, but it is not the time to take to output to the response. Okay, so response time is nothing but as soon as it is moving to the ready queue. Okay, as soon as it is moving to the ready queue, It doesn't carry that, it will get the CPU. Okay. So it will start responding once the CPU is allocated. There is a response time. Okay. So let us see one scheduling algorithm. Okay, there are several scheduling algorithms, preemptive and non-preemptive. Let us see one small scheduling algorithm. Okay, so one of the simplest and very simple scheduling algorithm is first come, first served scheduling algorithm, FCFS. In short, it is called as the FCFS. What is FCFS? So in the FCFS, actually the first come, first served scheduling algorithm is a non-preemptive scheduling algorithm. Okay, so in this scheduling algorithm, the criteria is the process gets the CPU. Which process gets the CPU? The process which arrives first. The process which arrives first will get the CPU first. Okay, the first come first serve scheduling algorithm. In the first come first serve scheduling algorithm, so the process whose arrival time is less, so that process will get the CPU first, and that means the processes are executed. The processes will get the CPU in the order according to their arrival time. Okay, according to their arrival time. For example, there are three processes, P1, P2, P3. Just assume the P1 or P1 is first enters the ready state. Okay, and then P2 and then P3. Okay, according to their arrival time, the CPU will be allocated, the CPU will be allotted to that particular process, and they will be executed in the same order. Okay, so we will get the CPU first. The process which is arrived first will get the CPU. Okay, so it is always non-preemptive in nature. Non-preemptive is nothing but, so until and unless the first process has been completed, the second process will not begin. Until and unless the second process is completed, the third process will not begin. That means the process will get executed in according to their arrival time. So first P1 and then P2 and then P3. Okay. So in the next session, we will be discussing, so we'll see some examples on this first scheduling, first served scheduling, FCFS scheduling algorithm. We'll see some numericals. So that is based on FCFS. Okay. So in that session, where we will be discussing how to calculate the total turnaround time and waiting time and uh, all those elements. Okay. So thank you. It is enough for this session.